what I need is so you have, oops, oh man, now I am in this. So you have a probe, and we talked about looking at a small structure here.
Yes.
And if it is full of calcium, the sound will come down from here. Oops. And it will cast a shadow. Yeah?
Yes.
Unless you're also seeing it by compounding. Because when the sound comes from different angles, then that bit is then not in shadow.
That's right. I'm with you now.
So you get a better picture with the compounding because you can see what's here.
Yes.
Behind the calcific thing. But if you use the fact that it's there, because you don't get a mathematical number, because you could see that was calcium by the fact that that was a brightness 10 or 8, as opposed to the soft tissue that is brightness 2. However, on most systems, most of the time, you can't see the difference between an 8 and a 4. Yeah. Have I lost you?
I heard your words, but I think you've lost me. Now you're talking brightness. You say on most systems you can't see the difference between brightness of an 8 or a 4.
Yeah, this comes on to something called maps. Are you familiar with the term map?
No, I'm sorry.
Okay.
M-A-T as in tango or M-A-P as in papa?
M-A-P as
Okay.
in a street map. So I am going to have to, I'm going to go, let's switch on to a different thing because I've not got that set up right. Just bear with me.
No worries.
I'm using 3 screens rather than 2. And it's all a bit confused. And so you have a grayscale that reads 1 to 20, maybe, or
Yes.
1 to 200. Lots of different levels of brightness. Yeah.
Yes. From white to black.
From white to black or black to white. Yeah.
Okay.
But let's go black to white.
Okay.
So 0 or 1 is a tiny amount of reflection, and 20 would be a lot of reflection. And that can be an absolute scale. You could have it as all the ones, as 1/20th of the maximum brightness was a 1, and 20/20ths was, so you could have a bone being a 20 reflector, being a certain brightness, and everything else in between as being less bright.
Okay.
But that doesn't actually give you a very good picture, because the vast majority of your echoes are down here in the 1 to 4 level. If you think of going through a boundary where there is no difference, you get 0 reflection, and a strong boundary between muscle and fat, you get 0.7% of the sound reflected back. Yeah.
Yes.
At a bony boundary, you get 43%.
How do you know this, or are you just coming up with? Anyway, it doesn't matter. Keep going.
Yeah. So you've got that thing. So as most of your reflectors are around the points, or most of your strong reflectors, the surfaces you want to see as bright, is around 0.7. So close, about 50 times smaller than the reflection at bone.
Yes.
So what you do is you have something that looks like a curve like that. So where the numbers, this is with increasing brightness, increasing strength of reflection, you get a small reflector there, and then you have your your strong reflectors there, and they get brighter and brighter and brighter. And then it doesn't really matter how much brighter you get. You have your really strong reflectors there, but they're not any higher up on that scale.
Okay.
Yeah. So instead of having a direct relationship between small and bright, between weak and strong signals, what you do is you make all the increase in the signal in your golden spot, in your golden area.
Yes, yes, yes.
Most of the change is. So then you can see the subtle changes between something that's a good reflector and a very good reflector.
I'm following you now.
Yeah.
And hard things like metal or anything like that, even if it would be at a 70%, it doesn't really matter because it's going to be bright.
Yes, exactly.
All right.
But that makes a difference. That means that you cannot see. The payback is that you can't really tell the difference between a little bit of calcium in the skin, in a soft tissue, and a reflector that's just maybe a place where where there is a good boundary that is very reflective.
Yes. Okay, I understand. So that because even though there's such a drop off there, that even if it could be really high, you're not going to see that big of a difference.
Yes, exactly. Whereas you can see the difference when it comes to calcifications in particular, because they cast a shadow.
Yes.
Yeah. Behind them.
Yes.
Because they back so much of the stuff.
Yes.
Because you lose essentially 43, almost 90% of the signal gets lost because the signal has to go through twice, through two boundaries. So you lose nearly all the boundary, all the signal.
That would be if it had a characteristic of a crystalline calcium as opposed to like a calcium hydroxyapatite or some level of not as reflective.
Yeah, not as dense.
Yes.
You know, this is the dense, mostly a density issue. You know,
yesterday I was taking a look at an elbow, and it looked to me like there was some calcification within the ulnar collateral ligament, and yet when I did the valgus stressing, I did not get a lot of laxity, and those the bright areas were along, like I would have expected some level of avulsive response from the medial epicondyle. But again, I think what you're saying is, and I'm not going to show you the pictures because you'd be knocking me down at the angle I came at that crazy thing. but you're saying if I would go strictly to B mode, take the compounding off, I could at least be assured that I would be able to tickle out what part of it is posterior acoustic shadowing or the shadowing from that. Yes?
That's the idea. Yes. That's what you have to be aware of on a machine that's using compounding. That where you expect to see shadowing, it's dependent on the size of it, and it's partly dependent on the size of it for different reasons. Partly it's slice thickness, partly it is it's because of this issue with the compounding, with the thing coming from either side.
Now, what part of this diagram is called map, or is it that
it is this? The shape of this curve is called a map, and you can get, and they have different shapes. You know that there are different shapes that are rounder or smoother, and that's one of the things that changes when you change your application. So when you go from musculoskeletal to gynecology, and it's where they've looked at where the money is in terms of being able to see the difference between things.
Yes, I understand that. What this basically shows is that they're attempting to establish a range between the grayscales, and they're making that range extremely precise in that particular zone, because there's large areas where we don't need the precision, and they just dump that off as not important to process.
Yes. So you're basically you're looking at how much we don't really care, or we choose not to care. We're not looking at different grades. There's the best reflectors in the soft tissues are less than 1% of reflection. The bone reflects at over 40%. You don't need any differentiation between 1% and 40%. So you just need, whereas you need lots of subtle differences between 0.4% and 0.8%. So you make that where the biggest change in your picture is.
Yes, I think that's well said, and I understood that. It's just, it's very difficult for me to understand how they can take a 1% margin and differentiate it so aggressively, because that's really where the interfaces lie in soft tissue.
Yeah, but you know, we do in a sense, we almost do the same. If you look at the electromagnetic spectrum, we just look in the one bit that's where we get all the where we have the strongest light. So we have developed a device that
that makes perfect sense. John, I would like to open it up to you to maybe free associate on what part of physics do you think is just not well understood by the MSK provider, and what part is the most important? Because I'm sure, I mean, you and I both know that it's everything about physics that our present point of care musculoskeletal provider does not understand. So I guess what I should say to you is, what is the area of your lecture? Or maybe you should bring that up, because I'm assuming you attempted to create your own map as to where the person learning MSK should be aware of physics.
It was more, my experience was that trying to teach physics, or trying to push physics down people's throats, is unsuccessful. You know, that without the support and without the time to bring it back, as we've been doing over the last few weeks, we've been biting at it bit by bit. I've always found, what I've found is it doesn't work when you just tell people it. When I lecture on it to very bright people, and I come back, I teach them to scan over a period of time, and then I come back and I used to do a little quiz to see what they remembered and what had gone in, and I'm very disappointing, the results. And these are people who are very good, able scanners and probably have a better understanding of physics now than when I taught them. But the problem is that all these parts make small differences, but it's an accumulation of all those small parts that matter. And so I don't have an answer as to what's most important. I think when you first start, most important thing is understanding anisotropy. Once you've got that, then I think it's more about understanding some of these other parts as to why the picture is the way it is, which, you know, obviously one of the things that's been overlooked the most, I guess, is slice thickness. But there's also all the other parts of what your resolution is made up of makes a difference. What happens as you change the other parameters, you know, just playing with the gain and its importance, and the fact that these maps are not a big part, but they make a big difference when you start talking about missing subtle things, like when we talk about rheumatology and seeing subtle inflammation in structures, or telling, heaven forbid, you get a cancer that's mimicking a cyst, and understanding why you have to manipulate when normally it's very obvious that something is a cyst and you just go, tick, it's a cyst. Why you have to stop and change the settings, change the gain in particular, because of this mapping, where things are of, because your maps, we've talked about what happens at the top end between a bright muscle boundary and a bone as not being that important. Well, there's also a tail on these, where where things that are very low echogenicity and things that are completely anechoic are actually described very similarly on the scanner.
Yes, and because that's been something you've alluded to, and it has the gravity of differentiating something that's sinister from something that just happens to be there. Can you address that a little bit as to what you do in order to, let's say, turn whatever is black on your initial scan into at least a critical refinement of what's there? And you had said gain twice now, John, and in our lecture that I failed to hit record on, you use something called time gain compensation, or TGC.
Yeah.
If you could briefly just touch on that a little bit.
Yeah. We talked about, if we start with the probe, and then you have your target close to the surface here, and your target right down at 4 centimeters. And these are figures that don't quote me on. But the amount of sound that is bouncing back off that target there, close to the surface of the probe, and the target there, this is, if this was 1,000 units, this would be 1 unit of sound that returned back. So
wow.
the signal at the top of the close to the probe is 1,000 times stronger. The same reflector, the same boundary between a tendon and the surrounding muscle maybe could be 1,000 times more powerful from the top of your screen to the bottom of the screen, and still be visible. And what the machine does is it measures how far that is, or takes how long it takes for that signal to go and come back. So the return journey of the echo there, and it then magnifies the signal coming back from here 1,000 times, based if that's what's needed to make these two signals equal.
Right.
It
again makes me feel like that lower one, in my amazement factor, that lower one has been singled out as needing to blow it up or zoom in on it, just like you were talking about with the map, where they had to pull out this critically small bit of information and blow it up as far as information. What you're saying is this is so small, but yet it is so important for us to have a differentiation in contrasts down that far that they have to pull that out.
Yeah, so it is just magnification. It is just an amplification. So it amplifies the signals in a sort of progressive manner. So the first signals are not amplified, and then as the longer the signal takes to get back, which relates to how far it is in the tissue, the more it's amplified.
So if you yelled against in a crevasse, and it took 3 minutes for your voice to get back, and of course that voice is quite a bit less loud, we would have to amplify it significantly for it to be the same loudness to your ear. So the longer it takes for that echo to return to you, the more we have to artificially increase the volume for it to be equal to the wall 4 feet away.
Yes, exactly.
Wow.
That is time gain compensation, which is what they call it. They compensate for the time it takes by increasing gain. Goes on in the machine and works in the background. What you often have on a device is a bunch of sliders going all the way down. You'll have seen on the large devices, there's a bunch of sliders down the side of the machine.
Yes.
That allows you to change the gain at any particular level in the screen. Yeah?
Yes, like a equalizer sound thing. Yeah, okay, I'm with you.
And it does that. And the classic example is if you are looking from one side of the bladder to the other. So you have a fluid-filled sac here.
Ah,
That
yes.
signal gets weaker and weaker and weaker as it goes through the soft tissues. But the signal that goes through the bladder actually maintains its strength, or goes through any fluid-filled structure without a lot of boundaries, typically, because it's boundaries. You're losing every tiny boundary. You lose almost 1% of the signal potentially, or something like that. And there are lots of boundaries in the body. So when you get a fluid, it goes in through much stronger. And so this area behind the cyst will be bright. And that's the enhancement artifact that you learnt about. And so what you want to be able to do, if you want to look at this in detail and not have it whited out in front of you, you can change the sliders here to make a difference.
On our Instamatic devices that I carry around that don't have the ability to change apertures or whatever, it was just a matter of doing a total. Well, I guess they have a deep gain. They have a surface, a middle, and a deep gain. And so that's just all that would be is turning the contrast down or the, okay.
Just it's turning the gain down. The contrast is something slightly different, but yeah, it's turning the gain down at the back of the picture. Or more often in musculoskeletal, we're looking at structures that have maybe been injured. So you're looking through an area where there's been bruising and bleeding in, and that's very fibrosed. So that would then be lots and lots of fibrous layers here, and this area would actually be darker. And then you would increase the gain, but you wouldn't necessarily want to drive around with the front of the picture also bright, because what you can do is you can just increase the brightness of the whole picture. But if you want to be able to have a comfortable picture to look at, you actually want to be able to change it, and this is known as time gain compensation. So that's what that is.
Very valuable, John. Can you take this drawing and talk a little bit about if you found a cystic looking device, or you can zero this out and how you refine it for whatever sinister content you were talking about before?
So you look at a lump, and I've probably got a case somewhere, but it'll take me a couple of minutes to find.
I'm perfectly fine with you taking that time.
But the story was basically it was completely black inside, and it was called a cyst, and it carried on growing, and it came back to scan, and so when we looked at it, it looked completely black, and then we turned the gain up, just turned the gain right up.
And when you say gain, you're not talking about these slider things. You're talking about the actual gain, the big.
Doesn't matter which one you use.
Okay.
Increase the gain, and suddenly it was full of little structures, and you could just see that it wasn't. And it was a very, very simple call, but this call was made in radiology. It wasn't.
Right.
There weren't beginners doing it. There weren't beginners doing it. They just saw what they wanted to, what they expected to see.
Now, you simply said that you turned the gain up. One quick question is, does that alter how loud or the amplitude of the actual burst from the probe, or is this post-processing of the normal sound that changes?
Post-processing of the normal sound.
Okay, and then the next question I have is, they should have done this, but again, I'm sure that whatever the reason was that their mind didn't do this.
Yeah.
Besides turning the gain up, are there other things like compressibility? Are there other techniques you use to refine these cyst-like structures?
Mostly, I just whack the gain up. It's a very simple. I also put color on. I also check the color.
And can you spend a brief bit of time again telling me why you prefer color over regular? Because all the texts, not all the texts, but all the ones that I studied for my certification over here, indicate the peculiarity of having the power Doppler be more precise at the low flow, or at what I would call microcirculation. And this is something we missed, and it was heartbreaking because you shared this stuff and I didn't save it. So
No worries. I do it partly, well, the main reason I use it is because empirically I've always found it, I've been much happier with the color on the machines I've used. I've found the color to be better than the power Doppler. However,
I'm gonna interrupt you, John. Empirically, for my small mind, must be in practice. You
yeah,
found it to just be naturally that way.
yeah, that
Okay.
was what I found. And so I then thought about it and thought, why is it? Because everybody tells you to use power. And every course I've been along and helped out on, they always say use power. And I find in practice it isn't helpful. I find that using sort of sensitive settings on a well set up scanner, the color Doppler, when you have a choice between simple color and power, which is the case for most of the machines that I scan on, the color is actually better if it's set up properly. My explanation for why that is because power is considered useful because it just measures the amount of Doppler signal. And I'm probably misremembering the exact terms and oversimplifying it. But where something is moving within your field, within the field that you're looking at, and the Doppler signals coming in, bouncing off the red blood cells typically, and all the signals that come back that show a Doppler shift, a change in frequency, are displayed. And as opposed to the color Doppler, where it's making an effort to quantify, to some extent, the direction that the flow is moving in.
I will have to tell you that, to me, the fact that it can take ambient expected frequencies and then all of a sudden be watching a different moving device, and it reads that at a higher or lower frequency, and we can then stink and color it, whether it's coming toward me or away from me, is just phenomenal. But what you're saying casually is that it has the ability to identify that moving thing based on the fact that it has established what the room looks like when nobody's in it, so that the motion detector now can tell something's moving. Is that? It's just amazing to me.
Well, your ear does the same thing though when it hears a siren go past.
Yes.
And tells whether it's going away or coming towards.
Racing cars or I hear you, but okay, I'm letting you continue.
But and because the power Doppler doesn't worry about the direction, it is thought, or people believe, that it then allows you to display more of the information more sensitively. And in theory, that is true. In practice, I find that the reverse is true. And that's because if I was looking at a vessel that was horizontal on the screen, the power Doppler would show the movement in their hair more readily than the color Doppler, because all the flow is running very close to parallel to the probe, and so the color Doppler has difficulty seeing it and picking it up. However, when you look at low flow in musculoskeletal structures, the actual flow is all like this, lots of different directions. It's never just parallel to the probe. And so I don't care about whether I see the flow going across the screen.
Yes.
Because for every bit that's going across the screen, lots going down.
Yes.
And because I'm looking for this flow here, any movement in my, if you have the sensitivity turned up so that you can pick up this horizontal movement, then you get lots of noise from all the micro movements in the hand and the probe and everything else. And so you get lots of noise in the picture. If you aren't worried about these tiny movements relative to the probe, which you pick up with the power Doppler, you can increase your sensitivity to pick up the flow, the easy to pick up flow that's passing, that is always passing in these windy structures in the microvascularity. There are always sections of it that are actually easy to pick up. And to pick up the really small ones, you need to turn the gain, the sensitivity up very high. But you don't have to do it as high, because you don't get as much noise with the color, because the color is looking only for these vessels. So when I'm looking for the complex microvascularity in a cancer or neovascularity in a tendon, I am going for the low-hanging fruit, the stuff that is actually going in this direction, because there is always stuff traveling in this direction. And by selectively targeting those, which I do with my color, I can then actually be more sensitive before any movement of my probe creates too much noise in the picture. So it is a complicated argument, but I find in practice it works.
Let me set this up in my own mind so you can see where I'm coming from. In the diagram on your drawing, where the arrow comes down from the probe, that is interrogating, that's just to identify structure. Overlying on this is an internal computer program or something that's reading. What is the difference in my oh, no.
No, you have we talked last time about your anatomical, your grayscale being 3 cycles. Do you remember we talked about this?
Yes.
You have boom, boom, boom.
Yeah.
And that's it. A pulse, a very short pulse, lasting 3 10-millionths of a second.
Okay.
So a tiny, tiny, tiny pulse. That creates your grayscale picture. So when you've got your color on, what's happening is you create a grayscale picture in maybe 1/40th of a second.
Yes.
And then this stuff switches off, and you create a different sort of pulse, which looks more like a sine wave with about 10 cycles in it. And that's a Doppler pulse. So
I had no idea, John. Keep talking.
So there are 2 completely different pictures that are being superimposed on each other, being made up with 2 completely different sound waves. So you have a sound wave that is 10 cycles long, so 10 10-millionths of a second, possibly or slightly longer.
Okay.
And they fire off in the same way. You get one, and then you get another, and then you get another, all the way along your picture. And that's why the size of your box is quite important, because the wider your box is, the longer it takes to update.
Okay.
So these pulses go off and they go in, which is why the color is has nothing like as good a spatial resolution as your grayscale picture. So the blobs are quite big.
Yes.
On your color picture, and that's because they're made up of 10 cycles.
Completely phenomenal to me. I don't even know where I would have learned this, because none of the books I've read even have this in there. So here's the thing that's troubling to me. We've established that these 10 sine waves that come from the Doppler interrogating pulse go down. I would assume that they're then taking a listen for the shift in that frequency when it comes back, in order to know whether that device is going away from or the red blood cells are going away from or toward me.
Yes.
My frustration is just like anisotropy in the case of a vessel that's flowing directly perpendicular to that. I don't understand how it has the ability to identify movement unless we're dealing with compounding waves of this. How does it tell the sideways movement?
It doesn't. You don't see sideways movement with Doppler. The reason you see anything at all is because if you're in a tube there and your probe's up here, you can either steer the box as previously discussed, which is what
Yes.
people do on their carotid things. And
Which is this? Which is these three? Yeah, it was phenomenal. I tried to explain it to my wife, and it was.
it, it's quite clever. But
Yes, it is.
in a standard box, when your box is square on your screen, the signal is just going straight down. Now, those blood vessels, the blood in there doesn't just go in straight lines, unless you've got absolutely purely
I'm
laminar
with you.
flow.
It's
And
throwing
so
some eddies.
you get a bit of, so you can, even when it's absolutely parallel, in theory you can see some, but in practice that's where your power Doppler is more likely to see it. But the truth is that in a big vessel that has laminar flow in it, or close to laminar flow, where it's all traveling in the same direction and it's hard to see, you can see the vessel on the screen, and you can either push the probe in a little bit further to get more signal, or you use an angled box to detect the movement.
I will tell you that I played with a vessel with my Clarius, and it was not in an angled box. And I brought it right to the center, and if one side wasn't blue and the other side wasn't red, John, I don't understand how they have the ability to take the center of my probe on, I think it was the ulnar artery, or it was the radial artery. And am I just wanting to see this? Because there's no way that they're going to be able to identify that the center of my probe had it coming from one way and going the other.
Now, it probably had more to do with the fact that your probe pressure was slightly bending the vessel.
Okay.
If you think the vessel, the edge, you might have had that, or it wasn't quite parallel, or you reach that balance point and it's getting signal back.
Yeah.
And it's guessing.
Unbelievable. But see, you can answer this with absolute certainty. I'm making it up to fit the picture. so keep going now.
Yeah. No, but so that is, so Doppler is quite complicated, and the physics is quite complicated. And
But you're just saying keep the power Doppler off, throw on the color Doppler, take it up to where it totally. What is your technique? Take it up until it is completely covering that square, and then back it off, or what is your technique?
The way that I've always done it, and presumably I was taught by my elders and betters, was that you change the scale, something called the pulse repetition frequency. And you adjust something called, it's sometimes described as scale, sometimes described as pulse repetition frequency. And the scale is usually demarcated on the side. You usually have a column on the side of your picture with red and blue colors. And then there's usually a number here, like 5 centimeters is typically what you'll see. And it's to do with, on your machine, you'll adjust it and it will be scale, typically. There'll be a button that just says scale on it. That's my handwriting, not great.
All right.
And you alter that. And I have found on most musculoskeletal scanners a number of between 3 and 5 centimeters per second is the optimum for most of the machines I've ever driven. So you take that down to somewhere between 3 and 5 on the scale, and then once it's there, you adjust the color gain, so your gain for the color, until you don't have too much noise. And then you also need to press very, very lightly. We used to always say, and I got it from a lady called Gina Allen, she would make me have a layer of jelly when I was doing color Doppler, visible at the top of the screen.
Oh.
Proved that I wasn't pressing.
I understand exactly what you're talking about, but what do you call it? You said you call it something because of her.
No. I just
Oh,
that's what we used to do. We used to she used to just insist that she could see some jelly at the top of my picture
yes,
before
fascinating.
the low speed and stuff.
John, I would not have a clue where you would change this number to 3 to 5.
Yeah.
I don't. Is it just non-existent anymore? Because I know they have slow flow and fast flow. Is that doing the same thing?
It may well be on your device. Every scanner I've driven has had an adjustment on the color. When you bring up color, it has an adjustment for when it has the display. There's always been a display there,
Yes.
and there's then a number at the top and the bottom.
Okay.
-5 or +/-7.
Yes.
And then one of the option highlights on the system is described as scale.
So that is the speed at which those items are flowing, and what you're saying is you bring it down to 3 to 5 centimeters per, I don't know, second or something like that.
Yeah, I bring it down to that those values. I would have to go back to my books to remember even what they do or what they're measuring. So I'm not going to bullshit you about it. But, it is 20 years.
We're getting close to the end of this, John, and my mind sees that we've made it about a third of the way through your physics lecture. I don't know what you have on the other end of that, but
I think we've actually got through the stuff. I wonder whether it's at hand, but no, they basically beyond that. There's 3 screens. Is 1 screen too many? If I stop sharing, we went through. Oops. So we talked about Scanlines. This is always one that I always used to test my students on. They never got it. The speed of sound in all the different structures. I don't think you really need to know that. Impedance mismatch, how the image was taken up, the difference between specular reflection and scattering.
I don't know anything about that, John. I need to have you bring it down to rubber meets the road for me, how that applies to my scanning.
Right. Well, you get a picture. It's how much it makes less difference to you than someone who looks at livers, as you'll see. But a specular reflector is a boundary, a large boundary, and the sound reflects back much as a ball does off a wall. As a scatter within a structure, the tiny boundaries that exist within every structure do not reflect in the same way. It's much the same as if you were playing a game of golf and you hit a golf ball against a wall, you'd expect it to come straight back at you. If you happen to be the wrong side of a copse of trees and you whacked it in through the trees, the ball would bounce off in just about any direction. Now, a sound wave isn't one ball, it's 100 or 1,000 balls, because it's every individual molecule within that structure. So when you get a small reflector, and small is defined as something that is close to the size of the wave itself. Okay. The length of a pulse, not the pulse, length of the wavelength of each individual part of it. When something's close to that, then the behavior of the wave as it strikes that structure resembles more like striking the bough of a tree.
Okay.
And the sound isn't reflected back in every direction. In one direction, it's reflected back in just about every direction.
Okay.
Sense that the thing rings rather than like a bell. And so only a fraction of the sound heads back towards the probe, as opposed to all the reflected sound, when you hit a large structure, all the reflected sound heads back in this direction. So you get 99% goes this way and 1% goes this way.
Okay, I have the concept.
when you get to one of these,
Yes.
99.9% goes that way. And of the small amount that is reflected, it goes in every direction. So only a tiny fraction of that goes in this direction.
This would be anything like a soundboard in a silent room where noise is reflected by foam rubber in various shapes and stuff?
It is essentially, but it is more like what happens when you drive balls through a forest.
No, I'm hearing you, especially if it's the same size of what it's striking.
Yes. Yeah. A ball hitting a big tree is likely to come back at you. A ball hitting a twig can go in any direction.
I'm with you on that.
So that's what happens. And so what you get, and this is a classic picture of an effusion in a chest. So this is the chest wall here. This is an effusion, a pleural effusion. You remember back to your hospital days, and this is the edge of the diaphragm. So the edge of the diaphragm is a nice bright line because it's a wall reflector, and the sound is going from the fluid to something with a different density, so you get a clear demarcation line. Superior
left, inferior right, or caudal, what is it, rostral left, caudal right, or?
The top is on the left side of the screen.
Yes. Okay.
Yes. On the right side of the screen. In the liver, and if your mother's ever made you eat liver, you'll know that there are no solid boundaries in it, but there's lots and lots of stuff in there. And all that stuff is actually very, very small reflectors. And so that's what gives it its texture. It's these tiny, tiny values. And you get this sort of almost smooth, homogeneous tissue here. And so that also makes up your picture. Now in musculoskeletal, you see this in the muscle. You see it in the texture of the fat. But it's less important. But this is essentially what you're looking for when you turn up that volume, when you turn up the gain, when you're making sure something's a cyst. Because you don't get this in a cyst, this slightly mottled, irregular pattern.
You're turning up the gain, which again you said is a post-processing event. It would be like turning up the brightness, because you didn't let me use contrast the last time.
Yeah, turning up the brightness. It's like turning up the volume on your stereo.
Yeah. Okay.
You are just saying any noise there, I just want to make it louder. And that's what you do. And even in this area here, because there is some noise within there, you can see a bit of noise here.
Yes.
That area, you'll get it. But when you turn it up in a cyst, you'll get used to, and if you always do it whenever you see fluid, always turn up the gain to where it gets uncomfortable, you'll see that it turns up in a very placid, very bland way. Soon as you get something that's got a little bit more texture to it, you will start to very easily pick up that it just doesn't look right. I saw the picture. I meant to show it you last time and then didn't. And then I saw it during the week. I was looking at some images and I saw a beautiful picture of where I'd turned the gain up on something to show that it was that there was synovitis when you couldn't see the synovitis around a biceps or something. And you just saw the rim just jump out at you. But next time I'll find the picture.
All right. I want to just I've got a I have to get to something on the hour, but I want to just assure myself of my understanding on the issues of that's the is this the evidence of the time gain compensation thing where it went through the cyst? It was expecting to go through denser material, so it heightened the location of what it is by turning up the volume.
Yeah. So it's basically this is normal tissue just around a testicle here, coming down here, and you can see it's just a very bland grey, and then suddenly this stuff behind the cyst, and this is an epididymal cyst, has just got really bright behind there.
I was thinking that's not a testicle there. That's a cyst near a testicle, like a varicocele or something like that.
Well, it's called an epididymal cyst. But yes, a varicocele would probably be somewhere down here. But yes,
you have too many brains for as short a hair as
And this here is.
Oh, don't go any faster. I want to go back through this stuff again, but I want to ask you this final thing, and then just stop it right there. We talked previously about the lateral dimension being a function of the probe type, that the axial dimension is a function of frequency, and that the elevation dimension is really a function of the quality of the probe, and they're getting that narrower and narrower. And I know that is something that you were, first off, were my assumptions correct on what I just said?
Yeah.
And so the slice thickness, will it ever get to a level of thinness to where it won't be a drum you're still beating?
I think probably yes. We're certainly hopeful for that. With the focus, with the ability to focus it more effectively, it will become less of an issue.
When a person names it the elevation dimension, do you think what they're naming is that we're looking down on a Google map and those are actual structures that are coming up toward us? It's just that's a two-dimensional image, and that's the elevation we're seeing.
I think that's probably a good description of it.
See, my simple mind needs to be able to see that I can actually put on the 3D on the Google map, and it throws shadows to give me an idea as to the fact that it's a little higher. And I'm thinking, because even back there a ways, John, you had said, and that's also a function of slice thickness when we were talking about how to differentiate small calcifications. And it still is one of those rooms I have to go into when you say slice thickness, and I have to go, now how is he varying that angle? Anyway, John, you've been very, very kind again, and there's more I want to talk about, and then one day I want to be able to feel better about myself, that I can throw pathology at you and risk having you go, Fritz, that's not calcification, that is density that comes from fibrotic material. I'm so sick of you mislabeling things on your professionally generated video. Anyway, John, I wish you the best of joy on your hauls, and that I hope you stay well. Are things feeling better over there, unlike the way I'm sure the media is telling you is happening over here in the U.S.?
Yeah, well, so I don't listen to a lot of the media, I'm afraid. But yes, it's things are slowly settling down a bit. But you know, I'm busy either way, so whether it's work or at home, and I just take it as it comes. But I'm hoping you guys are going to get your act together.
Yes, wouldn't that be nice? Wouldn't that be nice? You know, we're coming up against this election in November, and normally by this time it's all over the place with having debates and all this kind of stuff. I don't have any idea what's going to happen here, and it's just going to be a head shaker. Hey, I want to have you prep. What's that?
Someone's going to do something wild to get themselves elected.
And we're going to watch it. We're going to watch it play out. I want to have you come up with some kind of a theme song that you can play on your saxophone and on your guitar one of these days. John, have a great time. We'll connect again.
Yeah. Speak to you in a couple of weeks.
All right. Sounds good.
Yeah. Bye-bye.
Bye.